Okay, so I'll get started with today's lecture. And I am a bit of an idiot, and I forgot this last year. So we went through game theory number 1, and that lecture was kind of short. And this game theory number 2 is also kind of short. And this is the second year in a row that I have forgotten to just combine them into the same lecture. If all I did today was go through the slides, it would probably take about 20 minutes. So I could have put it at the end of last lecture. And I'm not going to waste your time and just arbitrarily take up time with the playing of this game that we're going to play, actually 2 different games. Hopefully that will be some sort of life lesson that you carry on with you beyond this lecture. But I do apologize for sort of not making those the same lecture because I meant to. And I always forget right until the last minute. So yeah, there won't be much lecture material today. But I have, last time we played this thing called the numbers game where you write down a number. Today you all have a piece of paper again. We're going to play 2 different games. So we're going to play that numbers game again, but don't write it down yet because we're going to talk about the game for a bit. And then we're going to play a second game. And one or more of those games may appear as a bonus question on one or more of the exams. Okay, so kind of pay attention to it because I think it's interesting, and it's like this weird life lesson in frustration in how other people think and how you have to sort of factor into how other people think into your decision for game making and stuff. So or decision making. So with that said, I'll get into the lecture slides, and so there's slides, then the game. Then I'll tally it up, and then the rest of the slides. Okay, so lecture number 9, game theory part 2, which is essentially just explaining what Nash equilibrium is. So last time we played this game called the numbers game or choosing numbers or whatever, and just as a refresher or in case anyone wasn't here, everyone secretly and simultaneously wrote down a number between 1 and 100 inclusive. And so then we're going to calculate the average number that was chosen. And the winner will be the person who gets closest to 2/3 of that average, right? And this doesn't mean the average of 1 and 100. It means the average that people actually wrote down. So if the average, that could be 20, it could be 50, it could be 60, right? So last time, these aren't the actual numbers from last time, and I know they're kind of small anyway, but they're from last year, and they were very close to the numbers, so I just saved myself some time and didn't copy and paste the things that we did. But it was very close. The winning number when we did it was 32, and in the previous year, the winning number was a 30. So in those results, which again aren't ours, but the time before, we had 34 numbers chosen. The average was 44. When we did it, it was 47. And 2/3 of that average is 29.5, and so 30 ended up winning. But let's do a little bit of analysis on this now that we have some time to do it, and now that we've gone through a game theory lecture. So, are there any dominated strategies in the numbers game? Hand up if you have an answer to that question. A dominated strategy, meaning that something else will always do better than that thing. Yep?
We can do a few things, like if you never go above 70 or you just stay under 50, that can be considered domination.
So, what is your answer then?
Always stay under 50.
So you're saying that staying under 50 is a dominated strategy? Or that you should stay under 50?
I should, it's not.
Okay, well, how did you come up with 50?
Because it's average, so even if we take...
Average of what, though?
Average of our range of numbers we can choose from. So even if we do something like 2/3 of 100, closer to 50 will always be better.
Okay, so that's one way of thinking about it. Anyone have a different answer? Okay, well, let's just, yep.
Numbers that people will choose, we can't anticipate it. It will be 1 or 2. It can be as large as 99. So we can't say due to the because maybe most of the people will choose a number from 1 to 10. Maybe they will choose like the bigger number. So there will not be any.
So just repeating the two answers for the video, because I haven't been very good at doing that. One of them was saying, hey, if we have this range of 1 to 100, let's think about the middle of those numbers. And so maybe we should stay under the middle of those numbers. And the other answer was essentially, we can't really predict what people will do, therefore there's probably not a dominated strategy. We have one more?
Yeah, actually last time around I observed that some people chose like 73, 74, but we can't go above 66, which is two-thirds of 100. So,
What do you mean we can't go above?
I mean, two-thirds of 100 is 66, right? So the number can't be above because we're taking two-thirds. So it can't be more than 66, so why go
So be very exact with what you're saying. What can't be more than 66? You're saying
the
it.
final number that you're trying to choose, right? Or predict, or so that can't go above 66 because you're taking two-thirds of whatever the average will be, and two-thirds, even if even if everyone chooses 100, the average will still be 100, and therefore the two-thirds of 100 would be 66.
Okay, now we're starting to think mathematically. So let's think mathematically, right? If everybody chose the maximum possible value of 100, that wouldn't be necessarily very smart, right? But if everyone chose the maximum possible number, then the average would be 100. And so two-thirds of the average would be 66.6 repeating, so we'll round it to 67, right? Therefore, the guess of 67 is guaranteed to be closer than everything above it, which is what you were trying to say, right? Yeah, so it's the same thing, just probably fewer words. So in this game, if we apply that level of logic to it, you know that if you choose 67 or below, you are guaranteed to do better than choosing 68 or above. There is no possible way, even if, like you said, we can't predict what people will pick. But even though we can't predict what people will pick, we can still analyze the worst case and know that there are some numbers that, if you pick them, you're just guaranteed to do worse than other numbers, right? So those, 68 to 100, we would call those dominated strategies, because picking 67 is better than them, always. Now, picking 50, being a dominated strategy, does not mean that any pick will be better than those picks, right? Because if the average ends up being 50, then choosing 70 is better than choosing 20, right? But a dominated strategy has that other component, which is actually saying what the thing that dominates it is. So everything from 68 to 100 is dominated by 67, okay? And similarly, everything 70 and above is dominated by 68, but that's not as powerful of a statement as this one is. Okay, now let's pretend that everybody who read that slide is rational, right? Do you see where I'm going with this? Can we keep going? If nobody plays a dominated strategy, which we learned is what you should do, then the strategy set, the things that we can choose from, is now 1 to 67. 67 is now the maximum number that we can choose. Uh-oh. Let's do some recursion. If everyone picks the maximum of 67, well, now the average is 67, and two-thirds of that average is 45. And so once we delete 68 to 100 as dominated strategies, 46 and above now become dominated by choosing 45. And we can go as far as we want to that, all the way down to 1, right? So what I tend to observe is that after people have seen these few slides, what happens is the numbers go down. I've never seen it go down to 1. Some people do pick 1, right? But how many? This is like a you know that I know that you know that I know that. How many times do you do that until you get to an answer, right? So this is called a rationality chain. And what you do is you say, okay, we're going to remove 68 to 100 if we assume the other players are rational. And then if we assume that the other players are rational and they also know that the other players are rational, then we go down another one and another one and another one and another one, right? And so I'm going to delete this last one because I didn't actually talk about mutual knowledge. So I'm going to just, because people sometimes ask what that means. So let's go back here. Okay, so you all have a piece of paper. Think about it for like 30 seconds. And we're going to play two games. So I'm going to get you to write on one side for the numbers game. And I'm going to get you to write on the other side for the next game that I'm about to explain. But the next game is a yes or a no. So I won't get confused with the two sides. So take 30 seconds, take a minute, think about it. What is your number going to be? But keep your pieces of paper because we're going to play another game right after that. And while you're thinking about that, I'll just announce that because today's lecture is going to be a bit short, I'm going to go right over to my office for office hours, so the people who normally can't make it can come over if they need to. But I am going to cut off the office hours at 5 because I'm not staying there for 3 hours for office hours. So if you want to, right after we finish, which should be in about a half an hour, then you can come right over for office hours then. Something else to notice about this game is that if everybody chooses the same number, everybody wins. Right? So if everybody decided, hey, there's probably a number that we can all choose where we all win, that's a thing that can happen. I've never seen it happen, but the thing is, everybody picking 1 is the same as everybody picking 100 because you're all the same closeness to the answer, right? But that will not happen, trust me. Don't think that everyone will pick the same number, but it is interesting to see how low you go, right? Okay, I'm assuming everyone has had enough time to think about that. Now let's look at the second game. This is called the investment game. The players, again, are everybody. And the strategy set, meaning the things you can do, are either invest $100 or don't invest. Now pretend that you're playing this game as if you have about $100 actually on the line, okay? We don't, right? But just pretend that those are the stakes of this game so that you actually put some thought into the process. So your choices are the following. If you choose to invest, if 80% of people also chose to invest, you win an extra $100. But if less than 80% of people chose to invest, you lose $100. But if you chose to not invest, you can't gain or lose anything. Okay? Now, this game appears all the time in real life, right? The stock market, right? If everybody starts buying Tesla, Tesla goes up, and then people want it more, so it goes up even more, right? It happens. I'm not saying to invest in Tesla. I'm not a big fan. But if people collectively start to invest in something, right? These speculative bubbles can form. More people want it. Like, Bitcoin went through the roof because of stuff like this, right? So if you don't choose to invest, you gain or lose nothing. If you do choose to invest, if a bunch of people invest, you gain money. If not, then you lose money, right? You may say to yourself, hey, everybody could just say yes, and we would all win, right? If everyone just participated, we would all win. Why wouldn't we do that? Well, it involves trusting that other people will actually do it, right? It's free money if you just write down yes. But, how many people? And so the interesting thing here about this game is it all sort of hinges around that percentage. If I change that percentage to 100%, I think everyone in the class would write no. If I changed it to 50%, I think everyone in the class would write yes. 80%, 75%, that's an interesting number. right? Because not everyone has to do it, but 4 out of 5 people have to do it, so now you have to think about it. And so another place, hand up if you think you have another example of where this can play out in real life. And if not, then I've got a couple of examples. Okay, so nothing right away. Maybe my example will inspire you. Okay, so I don't know if anyone was around at like sort of the beginning of Facebook, like 2007, 2008, 2009, when everyone was on Facebook all the time, right? It was crazy. It was like, you know, a few people had MySpace, but everybody was using Facebook. And something that happened, that still happens, but not so much anymore. And you know, I was in university at the time, so I was using it more often. But if there was any event, they would create an event on Facebook and invite everyone to the event. And what would you do before going to the event? You'd see who was going to the event, right? And if a bunch of people were going, you'd go. But if not a bunch of people said they were going, maybe you won't go. But if everyone just went, you'd have a great time. But now it's this, oh, should I go? I only know a couple of those people, you know, I don't know those people. It was this weird thing where like you were like checking to see if you should go rather than just going, right? And before Facebook, I had never seen that happen, right? Where people were like, I guess, you know, you'd call a friend, hey, are you going? Okay, if you're going, I'll go. But like not to the level where it was like, okay, 500 people were invited. 30 people said they were going. Oh, the guy throwing the party must be a loser, right? And so I'm not going to go. It was really weird. But it's kind of the investment game, right? If a bunch of people invest effort or their time in something, it will probably be successful. But if they don't, or if you're like worried that other people won't, sometimes it won't be successful. So it's one of these things that manifests itself in real life as well. So this has been the subject of a bunch of, not controversy, but discussion in Discord especially among the undergrads when I give this as a bonus question on an exam. Like for 2 marks, bang, right? And then people are just like, why didn't you say yes? And so there's like a yes versus no channel on Discord. But, so just write this down now, yes or no, and I'll write them both down and I'll calculate it and we'll play this game. But imagine that it was like $100. What would you say in this room of these people? So take 30 seconds, take a minute to write yes or no. And if you could pass them collectively to someone to bring up so I could start entering them in once you're done, that would be great. Did you not get paper? Okay, someone who has the extra paper. You want to pass it up? Oh, there we go. Perfect. Oh, you need something to write with. Oh, there's pens everywhere. See if everybody helps everyone. We'll be all right.
For this game though, is not investing choice, like no.
Yes or no is fine.
Not a blank though.
What's that?
Not a blank though.
No, it's yes or no. So write yes or write no. If you leave it blank, I will interpret it as no, but please say yes or no on the other side of the piece of paper. Thank you. Thank you. I'm not going to put down the yeses or nos yet, because I don't want you to see. Thank you. Yeah, I know, it's great. Just late anyway. Thank you. Someone didn't write a number. Who didn't write a number? You can just say a number if you didn't write one. Okay. I'm not going to call out anybody, but someone wrote no and 99. Yeah. I like this phrase, knowledge is chasing you, but you're too... No. Just let me finish. Knowledge is chasing you, but you're too fast, you know.
I got a problem with game theory, though. One of the problems is you're assuming rationality.
Yeah, but I mean, you didn't need to assume rationality of anyone else to know that 67 is always better than 99.
Yeah, but I also know I have like a 3% chance of actually getting it correct.
Yes, but so I made the mistake of assuming that everyone was going to act rationality for their own self and not assume rationality. But I'm not putting down intentional troll answers, so we're skipping that. Please don't intentionally troll the game. Try to win. It's also interesting to see the results of this game, graduate versus undergraduate. So I can see that attendance went down since the last class. Ooh. $18.5. And we have a 19. So who was the 19 before I have to go through and check? Okay. So what made you settle on 19? You don't know? Well, I'm glad you're learning something. It's my birthday, right? Yeah, that's what people usually choose. Okay, so I'm going to have a quick look. I'm just going to count up the number of no's, because that's the easiest way to do this. Lots of yeses so far. So how many of these are there? 5 to 28, 20, is that 23 or 24? Five. Oh my God, why can't I do this math? Yes, 24 things. And there are 6 no's. So it's 1/4 no's. So the no, well, the yes lost by about 5%. Okay? So, no $100 for you because a bunch of people, several people just decided to write no. But it's just interesting, right? Why write no when you could just write yes? Not saying it's right or wrong. Someone didn't like the end result of the game, so it's the first time I've had someone walk out. I'm just joking, but okay. So that I mean, what I'm going to say, I don't really have a punchline to that other than it's really interesting. And I think, like, years later, I meet students who I taught years ago, and they, like, mentioned this game to me because they were so frustrated or happy about the result on an exam, right? So, okay, so let's keep going. I got nothing else to say about it other than I think it's really interesting, and you should experience that at least once. So let's go back to this idea that we talked about last time of a best response. And the best response, why is that coming up there? Meant the best thing that you can do given your belief about what other people are doing. So if you fix the action of the other players in the game, and you can see that. What is your best possible thing that you can do in response to that? So we gave this example of a greedy player versus a caring player, and we said, okay, as the greedy player, alpha dominates beta, and then we look at the caring player, and the caring player did not have a dominated strategy. They did not have a best thing that they could do, but they knew through their analysis that they were playing against someone who did have a dominated strategy, right? And so if the other player had the best strategy of choosing alpha, then you knew that they were going to choose alpha, and so you would choose the best response to playing alpha. Okay, so that was the putting yourself in other players' shoes. And so Nash equilibrium is a concept where, and if you've so John Nash is what Nash equilibrium is named after, and there was a movie, Russell Crowe played John Nash. It's called A Beautiful Mind. It's a good movie. If you're interested in, the whole movie's not about game theory. It's about the drama surrounding his life, and he kind of went, he had mental issues, and it was really sad. But he became very paranoid and thought everyone was watching him, but I won't spoil the ending. But good movie to watch if you're interested in more about this stuff. So a Nash equilibrium is a strategy profile, and again, a strategy profile is this, right? It's everyone choosing an action. It's a Nash equilibrium if, for each player, their choice is a best response to all the other players' choices. That is the definition of a Nash equilibrium. There are other ways of looking at a Nash equilibrium, which I'll say in a bit, but the motivation for a Nash equilibrium is that there are no regrets. You cannot regret your choice if you are a player in a Nash equilibrium. Because if we hold the strategies of everyone else fixed, so think about it, I'm best responding to everyone else. So given they have done that, I'm choosing the best thing against that. If we apply that logic to everybody, then no individual player has any strict incentive to choose something else, right? If they had chosen something else, they are going to do the same or worse than the choice that they chose. So there cannot be any regret in your choice if you are part of a Nash equilibrium. And one thing that is a little bit confusing with the terminology here is that this person choosing 17, or whichever number that won, a single person's choice is not a Nash equilibrium, right? It's not a Nash action. It's not a Nash choice. A Nash equilibrium is a choice for everybody in which this condition holds. Okay, so it's everybody choosing something. And it is, if everyone is rational, self-fulfilling. So if everyone believes everyone else is going to play the Nash equilibrium, then they will also play a strategy from a Nash equilibrium. So let's look at an example of how to calculate a Nash equilibrium. So what you have to do is calculate the best responses first. So what is the best response of player 1 to player 2 choosing L? We go through the columns, and then we go through the rows, just like we did last time. So the best response for player 1, if player 2 chooses L, is to choose M, right? Because it's 0, 4, or 3, so we'll pick the 4. The best response of player 1 to player 2 choosing C is going to be U. R is going to be D. And now we do it for the other player. The best response for player 2 to player 1 choosing up is going to be L. So remember, player 2s are here. They're the second one. The best response to M is going to be C. The best response to D is going to be R. Okay? So what is the Nash equilibrium for this one? Well, we said that the definition of a Nash equilibrium is a strategy profile, meaning a choice for player 1 and a choice for player 2, or all the players in the game, where everyone is best responding to each other. And so we look over this matrix, and if we have 2 best responses, because we have 2 players, then that is the Nash equilibrium. But down is not the Nash equilibrium. Right is not the Nash equilibrium. Player 1 choosing D and player 2 choosing R, that is the Nash equilibrium. Why? Well, there's no regrets, because both players are best responding to each other there. They cannot do better by changing their action. Now, if more than one player changed their action, it's possible they could have done better, right? But if only one of the players changes their actions, they cannot do better. So let's do another example here. And this is how you would do it on an exam if I asked you to calculate a Nash equilibrium. So player 1, we're calculating the best response to player 2 choosing L. That is M. Now we look at C. Look down here. That is M again. And R is going to be down. Now we look at for player 2. So we fix player 1's action of up. We have 2 over here. There can be 2 best responses, right, if they're both a maximum. Here we've got M. We've got 1, 2, or 0, so it's C. And here we've got 3, 0, or 7, and so it's right there. So if I ask, what are the Nash equilibria for this? Oh, look, there are 2 Nash equilibria, right? So there can be more than one Nash equilibrium, and there can be no Nash equilibrium. So if I ask you on an exam, here's a matrix, calculate the Nash equilibria, what I would want you to do, essentially, and I'd explain this in the question, circle all the best responses, and then show if there are any Nash equilibria, where they are. How do we relate Nash equilibria to dominance? So here, for me, alpha, my choice of alpha is always better than my choice of beta, right? Because I look at the partner's alpha, it's 0 or -1, so alpha is better. If they choose beta, 3 or 1. So alpha strictly dominates beta in this case. Let's find the Nash equilibrium. So we circle our best responses for both players. There's the Nash equilibria in the top left. And a cool fact is that no strictly dominated strategy can ever be played in a Nash equilibria. Okay? So you can never be strictly dominated if you are playing a strategy from a Nash equilibrium. I feel really bad for the people who are just walking in because the lecture's over in about 5 minutes. So I apologize for that. Also, more than one Nash equilibrium can exist in a game. Weakly dominated strategies can be chosen in a Nash equilibria, and here's just an example of that. And in a Nash equilibrium, no player can do strictly better by changing their strategies, but you could do as well if you change your strategy. Okay, and one other fact that I forgot to make a slide for, I said sometimes no Nash equilibrium can exist, right? So if I go back here, you could probably very easily create, put a bunch of numbers in here such that there's no best response in the same place for both players, right? However, there's a type of game called a zero-sum game. And it's the intuitive explanation for a zero-sum game is in order for you to lose something, or in order for you to gain something, someone else has to lose something. So in a game of chess, the result is I win, and in order for me to win, you have to lose. There could also be the zero outcome of drawing, but both players can't win, right? If you're thinking about poker in a scenario where there's no casino taking a little bit of the money, in order for me to win $30, everyone else has to lose a collective amount of $30, right? Those are called zero-sum games. And in a matrix form of the game, all the utilities or all of the payoffs are going to sum to 0. Okay, so if we have a matrix where everything sums to 0, we have another property which is in a zero-sum game, it is guaranteed that at least one Nash equilibrium exists. Okay, so it's interesting, but I forgot to put a slide there. And the investment game, which we just looked at, let's talk about a Nash equilibria. Okay? What is the Nash? Well, when I say the Nash equilibria, there could be none, there could be 1, there could be 2. What is a Nash equilibria if it exists for the investment game? Hand up if you think there's none, or name one if you think there is one. Yep.
The state where at least the percentage specified that people votes yes or above?
So you're saying, for our case, any strategy profile where everyone chose greater than 80, where more than 80% chose.
Yeah, whatever the version.
Now, let's look at the definition for a Nash equilibrium, because on the surface, I think that's intuitively sounds good. But in a Nash equilibrium, no individual player can gain by changing their vote. So if it was more than 80, but less than 100, someone who voted no could change their vote and gain the money. So that would not be a Nash equilibria for the investment game. So keep that in mind. Think of it that way. No single person who changes their vote can gain in a situation where it's a Nash equilibria. So are there any? Yep.
I just had a question for that one. Where we gave the answers to you, technically we couldn't really change our answers? So we couldn't change our vote?
Well, I mean,
Would there be a Nash equilibrium in that instance?
what I'm saying is if you drew out the matrix for the game that we played, it's a huge multidimensional matrix because it's a complex game. What I'm saying is it has nothing to do with the physicality of a piece of paper being given to me. But what I mean is not changing the vote, but if they had chosen something else, could they have done better, right? So in a Nash equilibrium, if anyone had chosen another thing, they would either do the same or worse if they had chosen something else. So let's not talk about, okay, once the game is played, you can change, but if they had chosen something else, that's probably a better way. Think about this. What if nobody invested? If nobody invested, if a single player had chosen to invest, would they do better? They can't do better because all of a sudden they're out $100, right? Where they would have been out $0. So nobody investing is a Nash equilibria. Everyone investing, well, okay, if everyone invested, if any single person changes their vote, they're doing worse because they're not gaining anything where they were gaining 100. If you are assigning just numerical payoffs to the dollar amount, right? So there are two Nash equilibria here. Just because there are multiple Nash equilibria does not mean that you're going to get the same payoff from being in one of those Nash equilibria. And it doesn't mean that your best possible outcome comes from being part of a Nash equilibria. Because the one where nobody invests, well, that's obviously, you would rather be a part of the one where everyone invested because you'd get more, right? If your payoff is your actual utility. And so being a part of a Nash equilibria does not mean it's the best thing. It just means you cannot gain by changing your particular vote in that game or your action. So that is the Nash equilibria. And the Nash equilibria for the numbers game, I'll leave you to think about that one. Okay, numbers game, is there a Nash equilibria in the numbers game? Well, just think about that one. So, possible exam questions, definition of a Nash equilibrium. There are a couple of different definitions that are kind of equivalent. Calculate the Nash equilibrium for a given matrix, and maybe explain the Nash equilibrium for the numbers or the investment.